Hello and welcome to the Harvard Radcliffe Institute. My name is Claudia Rizzini. I'm the Executive Director of the Fellowship Program. The Institute is one of the world's leading centers for interdisciplinary exploration. We bring students, scholars, artists, and practitioners together to pursue curiosity-driven research, expand human understanding, and grapple with questions that demand insights from across disciplines. You can be a part of this vibrant community by attending public programs such as this one, visiting virtual exhibitions, or pursuing the special collections held at the Schlesinger Library. To learn more, you can visit radcliffe.harvard.edu and sign up to receive more information on news and events. We'll begin the program with a presentation by Merav Opher. After the presentation, the speaker will respond to questions from the audience. Please use the Q&A feature on Zoom to submit your questions at any time throughout the program. We ask that you keep your questions brief to allow us to address as many as possible in the time that we have together. It is my pleasure to introduce the William Bentinck-Smith Fellow, Merav Opher. A professor in the Department of Astronomy at Boston University, Merav Opher is interested in understanding the cocoons around stars, called astrospheres, and generated by the stellar winds as they move through the interstellar medium that surrounds them. In particular, her research focuses on understanding the heliosphere, the cocoon around the solar system, which creates the foundation to identify habitable astrospheres. At Radcliffe, Professor Opher is continuing her groundbreaking heliospheric research. She is tackling questions such as, what is the shape of the heliosphere? Is it a long-tailed comet-like shape as described in the classic view, or is it a croissant-like shape as her recent work suggests? And what is the physical mechanism driving the shape? Understanding the shape of the heliosphere is the first step to grasping the shielding properties of the heliosphere. The results of this research will allow for the broader astronomical community to apply insights of the only known habitable astrosphere to other stars. Through this work, Professor Opher dares to ask and search for the answer to the question, are we alone in the universe? The outcome of her research will allow scientists to predict which other stellar system had the potential to harbor habitable Earth-like planets. Born a twin in Israel and raised in Brazil, Professor Opher gained her PhD in astrophysics from the Universidade de São Paulo. She came to the United States at the age of 29 and is open about the challenges she faced as a foreigner and as a woman in the sciences. Despite these difficulties, Professor Opher has had a decorated career, winning numerous awards, including the 2007 Presidential Early Career Awards for Scientists and Engineers, and the 2008 NSF Faculty Early Career Development Program Award. She has served in many capacities in several major NASA panels, such as the NASA Heliophysic Mission Senior Review Panel in 2015, 17, and 2020, that judges the portfolio of NASA missions. Recently, she became the principal investigator of the Shield Drive Science Center, a NASA-funded center with more than 40 leading scientists across the dozen institutions. And now it is my pleasure to give the floor to Merav Opher.
Thank you so much, Claudia, for the beautiful introduction. And I wanted also to thank the Radcliffe Institute, and the Radcliffe Fellows are amazing. It's been an incredible year. And also my Radcliffe Fellow, Daniel Abdullah, that has been a pleasure to work with him. So the story I'm going to tell you today will use data from the depth of the oceans, shown here on the left, to data at the edge of the solar system. So all the way from the deep oceans to the edge of the solar system, to try to infer what happened in the climate and perhaps in human evolution 2 to 3 million years ago. So to start our journey, I need to tell you what are astrospheres. So when you look up in the sky and you see beautiful stars, beautiful luminous objects, you don't realize that every single star out there is surrounded by a cocoon. Those cocoons we call astrospheres, and they are formed by the wings of the stars as the star moves through the surrounding media. And here are several examples from nature of the different flavors and shapes that astrospheres come. Why do we care about astrospheres? Astrospheres in general are larger than the planets that go around the star. So they are much larger than the stellar systems that they housed, and they protect from material that come from the galaxy. So if we want to find an Earth-like analog, as Claudia was describing, and we would like to, we need to understand the properties of astrospheres, how they shield material. We have an understanding of the shielding properties from our own heliosphere that surround our sun from measurements like I'm showing here on the right. We sent a spacecraft called Voyager in 1977, and it's still working. And in its journey towards the edge of the heliosphere, it's measured galactic cosmic rays. And galactic cosmic rays are energetic particles around GeV in energy, and they're very hazardous. They're in particularly the #1 hazardous for astronauts that venture outside Earth to the moon, to Mars. We need to really understand how well our heliosphere shield galactic cosmic rays. And as you can see in this data, Voyager, throughout the years, as it's moved across the heliosphere, measured an intensity that went down, up, down, until it's arrived almost to the edge of the heliosphere. And then it's left the heliosphere in 2012 when the intensity jumped by 75%. So you can see how important the shielding properties are to protect us. And the heliosphere is the only known habitable astrosphere. Of course, we want to find another Earth analog, and I hope there are more habitable astrospheres out there, but we haven't found yet. So right now we only have one data point that is our heliosphere that is habitable, of course. And we would like to understand the properties of the astrosphere, of shielding, and etc., to really characterize the role of the astrosphere in the development of life. The story I will tell you today will look in the heliosphere, not of today, but 2 to 3 million years ago. And at that time, you will find later on in the talk, we were not inside the protective shield of the heliosphere. We were actually outside, not just us, but the rest of the planet unprotected. And this had an incredible effect on the climate at the time, and we think to human evolution. So before I start in this journey to tell you this story, I want to share a picture and a poem with you. So the pictures show me and my sister. As you heard from Claudia, I was born in Israel. In the age of 8, we moved to Brazil. So here we are with our Israeli outfits, standing at the radio telescope where my dad, standing behind me, used to observe. The reason why I'm showing you this picture, because I think the fact that I was born in Israel, raised in Brazil, and then moved to US, gave me a toolbox that I carried with me to able to go from discipline to discipline and apply my knowledge and transit between disciplines, between space physics, astronomy, climate, very much like you have to transit between cultures. The other thing I wanted to share with you before we start on the science is a poem. This is from a poet that I adore called Elizabeth Bishop. I think it's very fitting to the Radcliffe Institute that has so many amazing poets. And it goes, is it lack of imagination that make us come to imagine places, not just stay at home? Or could Pascal have been not entirely right about just sitting quietly in one's room? Continent, city, country, society, the choice is never wide and never free. In here or there, no, should we have stayed at home, wherever that may be? And I love that point because Bishop talks about what is home. Can we recognize even what is home? And a lot of my research carry that displacement, that search of what is home on trying to understand the heliosphere, our home within the galaxy. So how did we learn about the heliosphere? We learned from missions like Voyager. Voyager is a huge mission. I will show in a bit the size of it. And Voyager was launched in 1977. And I grew up going to the library and seeing these incredible pictures of the first images of what other worlds than us look like. Uranus, Saturn, Neptune. With Voyager, we learn that there are volcanoes outside Earth. Voyager also, now you can see the size of Voyager. This is a true replica of Voyager in the Jet Propulsion Lab, and it's ginormous. And one of the things that is beautiful on Voyager, that is also carried a golden record. The golden record was assembled by Carl Sagan and his wife, Andrienne. And the idea behind it was to collect all the music, pictures, images, poems that will tell for an extrasolar being that will encounter Voyager. Years after Voyager will shut down, will not be able to send data anymore. And that golden record will tell that extrasolar being what humanity was all about. So there are pictures of music sheets, of our DNA, of scientists looking, and there are greetings in many languages. I'm going to show you one of them.
Hello from the children of planet Earth.
And now Voyager 1, there was two spacecraft, Voyager 1 and 2, are at a distance 156 astronomical unit. If you're not familiar with distances in astronomy, astronomical unit is a distance between us and the sun. Voyager 1 left the solar system, Voyager 2 also left the solar system, the heliosphere, and they are at a distance 156 and 130 astronomical unit. And I'm giving you these numbers so you can realize how large is a heliosphere. It's really big. And we learned from missions as Voyager a whole lot about the heliosphere. One of the things that we learned that my group led back in 2006, and then we published in 2007 and 2009, the fact that the nose of the heliosphere, the region where we are slamming against the galaxy, was distorted. The northern hemisphere was different than the southern hemisphere. The southern hemisphere was pushed in by the magnetic field that came from the galaxy. And we could sense it from the Voyager measurement, even though Voyager was inside the heliosphere. We could sense that the nose was distorted. And what was nice that later on, there was a different mission, IBEX, that took the first images in 3 dimensions of the heliosphere and showed the influence of the interstellar magnetic field. So this was well accepted afterwards. But there are many, many, many other challenges. And as Claudia mentioned, I'm leading a drive center. It's one of the largest centers that NASA put together. And it's housed more than 40 scientists. We have more than a dozen institutions. And the goal of that is to tackle important problems in space physics that require lots of eyes, lots of people working together. And I'm not going to have time to go through all the challenges, but I wanted to impress upon you the complexity of trying to understand the heliosphere. So we have scientists looking from microscopical phenomena, how particles go and travel and create turbulence, to scientists that look large scales. We also have scientists, not just from Voyager, but also scientists from other missions like New Horizons, IBEX, Cassini, all of them giving invaluable data for us to try to understand the heliosphere. One thing that I just want to give you a taste of the challenges is number 1, that is a global structure of the heliosphere. So there is a whole debate within the community, what is the shape of the heliosphere? Again, why this is important? Because the shape is directly related with the characteristics, how well the heliosphere shields us. If we are not being able to even describe how big we are, we cannot describe the shielding properties. And here I'm showing you 3 different models, one from Moscow University, one from my own group at BU, and one from University of Alabama. We are all debating the different shapes of the heliosphere. And now I'm going to show observations from Cassini in high energy and from IBEX in low energy. They're all giving us energetic neutral atoms observations. And they also interpret the data in a different way. Cassini interpret the data saying the heliosphere is spherical, while Ibex say, no, it's consistent with a comet-like shape. So what is the answer? And we know that astrospheres comes in all sorts of shapes and flavors. Look at the different shapes of astrospheres that we have images in astronomy. We would like to know what our own heliosphere look like. And this idea haunted theoreticians from the 50s and 60s. And here I'm going to show you one of the jewel of a paper that was done by Eugene Parker in 1960. And the problem of imagining what is the shape of the heliosphere has to do with the fact that we know the output of the sun. We know the pressure that the sun sends out with its wind. What we don't know is the pressure that comes from the galaxy. And one of the biggest unknowns is the magnitude and the intensity of the magnetic field from the galaxy. So Parker imagined two extremes. One, when the magnetic field from the galaxy was non-existent, negligible, and then the sun would be at the center, having a wind that blow, and then go to a long tail in the back, and forming this red shape heliosphere, a comet-like. On the other extreme, he imagined, what if the magnetic field of the galaxy so strong that it overwhelmed the wind of the sun, and then the heliosphere would look like a tube. And the community ended up settling in a comet-like shape for no particular reason. If you Google heliosphere, you see the beautiful picture that NASA put together where the sun is at the center, the planets go around, and the heliosphere is much larger in a comet-like shape. And one of the reasons probably that people settled on that is because the first simulations that neglected the magnetic field gave a comet-like shape. So my group came in 2015 and shaked a little bit this paradigm, but realizing that there is another ingredient that people had forgotten to take into account. And that ingredient is a magnetic field of the sun, its own magnetic field, the star's own magnetic field. Why it's important? Because when you have a star that has a wind that blow its magnetic field, here I'm showing you in yellow, the traditional assumption that the magnetic field is negligible. The wind goes to the edge of the heliosphere shown here and form a long comet-like tail, and the magnetic field just go for the ride, like a marker. However, the magnetic field is an interesting creature. It's very much like a rubber band. If you take a loop of a magnetic field and try to stretch it, it's going to resist. And that resistance, the same way as a rubber band, is due to its own tension. Magnetic fields don't like being stretched. And the reason that the assumption was being made to neglect the magnetic field from the sun had to do that if you look at where the energy is, at the edge of the heliosphere, it's all in temperature. The wind is super hot with a temperature of around keV or 10 to the 7 Kelvin, if you're more familiar. It's very hot. So when you look how much the magnetic field contribute, not much, we can neglect. However, we realized in 2015 that the very flows of the solar wind that try to stretch the magnetic field had a comparable energy to the magnetic field. So the magnetic field will not allow it to stretch. And we made a simulation shown here on the left, where the sun is at the center, the magnetic field is in white. And you can see that those loops of magnetic field are not being stretched towards forming a long tail. They actually resist the stretching and become the backbone of the heliosphere. And I like to think like a toothpaste. If you're squirting a toothpaste, the walls of the toothpaste will resist, right? So the toothpaste will squirt up and down. And this is the same thing that happened in the heliosphere. The solar wind cannot pull the magnetic field down the tail and ended up squirting out into jet lags. So we found that the star make jets. And the shape of the heliosphere, it's a croissant-like. We coined it croissant, where the interstellar wind goes in between the two jets. This was a major shake for the heliosphere community. They didn't know what to do with that. And again, this is an example when two communities should talk to each other. In astronomy, the neighboring community, they know about that. They have seen jets confined by magnetic fields. Look at this example of a radio galaxy, much larger than a star, forming two jets. And the radio galaxy is not static, very much like the sun, moves through the interstellar medium, making the jets bend backward and look very much like the croissant that we have seen in a smaller scale for the sun. A couple of years later, I had a sabbatical at Harvard and CFA, and I started working with Habitable on extending this work. And what we did was to describe the solar wind in a more advanced way. In general, models characterize a wind with one density and one temperature, like this one on top. However, we know that the wind that the sun has or emit from the surface all the way out has at least two different densities and temperatures. It doesn't have one density and one temperature. Has a very hot component that I told you, a keV, 10 to the 7 Kelvin, and also had a very cold component around EV, 10 to the 4 Kelvin, and they don't mix, very much like water and oil. So we made a simulation with that, and we found, again, the magnetic field confined the solar wind, create two jets, but the nose is much smaller. You can think like a petite croissant, smaller, deflated croissant. Nature Astronomy ended up picking it up as a cover, call it crescent-shaped heliosphere, and it showed the excitement of the community of trying to understand this important question: what is the shape of the heliosphere? We think there is a change in paradigm. It's not a comet-like shape, but it's small, and it's a croissant-like. So what did I do this past couple of months in Radcliffe? In this fellowship, I took the knowledge that I built around the heliosphere and space physics and look back in time. Why back in time? I could have taken that, and I hope I will, take the same knowledge and look in the future, how the heliosphere will be in the future. But I decided to start working 2 to 3 million years ago, again with Avi as my collaborator. And the reason for that there is interesting data, both from the depth of the ocean and both from the human evolution, pointing that something different happened at that time. And we actually thought that the Earth was not inside the heliosphere, but out. Why? So the data is the measurements of the isotope iron-60. Iron-60 is not produced on Earth. It's produced on massive stars. When they die, they explode as supernova, and they deposit it in the interstellar medium. One thing to realize, iron-60 has a half-life of 2.6 million years. The Earth is much older than that. So if we detect iron-60 at Earth, it had to be deposited after Earth was formed. It's not from the original matter. And actually, iron-60, due to this new high-precision accelerator mass spectrometer, was detected in several papers, but in particular, the last one, we're really able to narrow down the signal all the way in ocean samples globally, also in ferromanganese crust, in Antarctic snow, in galactic cosmic rays, and also in the moon, in lunar samples. And all of them give a clear signal of two peaks. One, between 2 to 3 million years, and another one between 6 to 7 million years. The question is, what brought iron-60 to Earth? So there are several suggestions, and in particular, the most popular one is that a supernova, or maybe several supernovas, exploded outside the heliosphere. I'm showing you a figure from Brian Fields et al. That show a supernova. And remember, the supernova is the death of a massive star. It's a catastrophic event. It's a huge explosion. And I'm going to give you a unit, parsecs. Parsecs, it's 100,000 of astronomical unit. It's much larger. But in astronomical scale, it's pretty close to us in the interstellar medium. So they suggested that if such a star will explode outside the heliosphere, it's going to push the heliosphere in and going to almost arrive to Earth, shown here in a circle in black, and deposit iron-60. This is an interesting scenario, but it's challenging because you cannot explode, you need fine-tuning. You cannot explode it too close, like 8 parsec, then you kill all life on Earth. And we're here, so this didn't happen. If you explode a little bit farther away, then you have a problem that you don't have enough energy to really shrink the solar system. Then you need to make assumptions and rely on secondary mechanisms like dust to bring iron-60. So when I started working with Avi, we started thinking on a simpler explanation. What about the heliosphere on its journey, meeting a neighboring cloud that made the heliosphere shrink? So in order to explain to you what do I mean by a neighboring cloud, let's look at the medium, the interstellar medium around us. So welcome to the neighborhood of the sun. So the large neighborhood of the sun, and now I'm talking about 200 parsec. This is again, parsec is 100,000 times the astronomical unit. We live in a huge bubble that actually just this year, the CFA folks, led by Zucker et al., published the latest beautiful paper on how the local bubble look like. And the local bubble is a low density cavity that probably was formed 20 million years ago. And the density of, it's mostly hydrogen atoms that is very low. It's 0.005 hydrogen atoms per centimeter cube, if you can picture it. And it's very hot, 10 to the 6 Kelvin. So we're here. But we are moving, we are not static. And our motion is 18 parsec per million years. So people like Radcliffe and Linsky map the very local neighborhood, not on around 200 parsec, but around 15 parsec. And they found a whole collection of clouds, more massive than the local bubble, around 0.1 hydrogen atom per centimeter cube, and a little bit colder, 7,000 Kelvin. So you can imagine that as the sun moves with 18 parsec every million years, it's going to encounter a whole lot of different clouds. And in my community, the heliosphere, we know that encountering different clouds has a strong effect. Because the heliosphere, after all, it's a balance between the output of the sun and what comes from the galaxy. So nowadays, we have this shape, like I told you, the petit croissant. This is a cross section, size of 100 astronomical unit. But we live within a neighbor not supermassive. Again, 0.1 hydrogen atoms per centimeter cube. And there are people in our community like Hans Müller et al. That simulated what will happen if the heliosphere will encounter a cloud 100 times more massive, like 15 hydrogen atoms per centimeter cube. The size of the heliosphere will shrink to 23 astronomical unit, more or less a trajectory of Uranus. It's not enough to bring iron-60 all the way to Earth. So we asked the question, what will happen if the heliosphere will meet much more massive, a compact cloud that perhaps exists in our neighborhood, but has 1,000 hydrogen atoms per centimeter cube? And the question, does this type of cloud exist? And I want also to give a nod. There are old papers by Martin Ries and Begelman, by Hans Farr and Yaki Khan, imagining meeting the heliosphere with massive clouds, in this case, where stars are formed. But we were asking not where stars are formed, but in our very local neighborhood. In fact, there is a star, there is a cloud like that. There is one called local Leo cold cloud that is located between 23 to 45 parsec. Again, remember our motion is around 18 parsecs per million years. We could have crossed that cloud. In fact, Hod in 2010 found that the local Leo cold cloud could be part of a huge ribbon that he called the local ribbon of cold cloud, shown here. Many cold clouds that span a whole large portion of the sky. Any of these clouds could have met the sun. In particular, we are going to use the local Leo cloud as our example of a cold cloud. And Mayer et al. Found that its density is what we were looking for, 3,000 hydrogen atoms per centimeter cube. So we roll our sleeves. We took the state-of-the-art arsenal that we have to describe the heliosphere, and we simulated what will happen if the heliosphere will meet such a massive cloud. We had to also assume what the speed of the cloud will be, because it depends on the relative speed that the sun is moving to the cloud. So we know the direction and the speed of the sun, and we calculated which speed local Leo cloud had to have such that it will intercept the sun 2 to 3 million years ago. And we found that its speed, it's around 14.5 kilometers per second, very much typical like the clouds around us. Great, so drum roll, what we found, voila. We found a heliosphere that shrank well within the trajectory of Earth, that is 1 astronomical unit. The heliosphere at the nose shrank to 0.2 astronomical units, meaning that all the planets in the solar system were not inside the heliosphere, but in the cold, massive interstellar medium. So that iron 60 peak should be not just on Earth and the Moon, but in every single planet out there. So this is the nose. The tail, what is interesting, was a long comet, because the magnetic field at the time didn't have the right geometry to confine it. So we had a long tail, but a short nose. In 3 dimensions, it looks like this. This is a heliosphere where the trajectory of Earth intercepts the heliosphere. Sometimes it's inside the heliosphere, but most of its trajectory, as well as all the other planets, were outside. So it's interesting. Sometimes the heliosphere is not able to protect us. And one of the consequences that we ask ourselves, what were the consequences for the climate at the time? So what we were interested is to know what people know about climate back then. This is called paleoclimate, and I was fascinated to learn all about it. There are those organisms called foraminifera, or forams. They have shells, and the shells have structures that they basically add rooms, like you add rooms to the house. They expand the shell as they age. So you can look at the shape of the shell and know where that foraminifera was formed. So people do that, and they live and they end up dying and dropping to the depth of the ocean. So people take samples, look on their shells, and figure out the time. So you can see here age, and they're able to map back into 60 million years ago. What they do, they look at the ratio of isotopes O18 and O16. O16 is much lighter than O18, and as the depth of the ocean becomes hotter, O16 evaporates. So if you have a high ratio of O18 to O16, it means that the ocean was cold. And you can look back in time and realize that the oceans were much warmer, here's temperature, than today. What we were in particular interested in the 2 to 3 million years ago, when there is a rapid decrease. Earth became fast around 2 to 3 million years ago, much colder. So the question is, if that encounter with a cold cloud that can explain iron 60, can it explain this drop in climate, this cooling? So in fact, it can. And there are works like Thomas et al. And McKay and Thomas and Yabushit and Allen that looked into it, looked what happened when you have 3,000 hydrogen atoms raining on you. And when you look at the Earth atmosphere and you dump 3,000 hydrogen atoms, what you will end up doing is depleting ozone in the mid piece of the atmosphere. It's called mesosphere. You deplete ozone, you create a whole large amount of hydrogen of water. And because the mesosphere height drop, this water become ice. So you form globally a whole global sheath of ice clouds. That global ice clouds cool down Earth. So this is nice because it's mean that an encounter with a cloud can explain that drop in temperature and can explain iron 60. When we looked at paleoclimate models like these ones, trying to see, do they include such effects? They don't. They include the fact that the Earth's tilt change with time. So as Earth orbits the sun, there is more or less radiation coming from the sun. And this is an effect on around 40,000 years, not 2 to 3 million years like we're looking. So models, paleoclimate models, again, the issue that disciplines live in silos. They don't include the fact where Earth and the solar system were in the interstellar medium. So I hope I convince you the importance of going between disciplines and looking how the heliosphere could have affected and perhaps will affect climate. Now, the last piece is, did it affect human evolution as well? It's not a new idea. There are a couple of works and they're summarized in a National Academy report called Understanding Climate Influence on Human Evolution. And I'm taking here a figure from Peter de Menocal in Science in 2011 that summarizes the argument. The argument is that the human evolution around 2 to 3 million years ago started splitting in two branches. This is a time when Australopithecus afarensis, or Lucy, this one on the right, went extinct. And the Homo lineage appeared. Appeared also the first evidence of stone tool. And when you look at the vegetation at that time, and you can figure out the vegetation, this is again another incredible story, by looking at plant wax biomarker on soil carbonate, and you can tell that in Africa at that time, the climate was much more arid. This is also the first appearance when hominin were not just in Africa and started migrating. So people like the Menocal and also Potts in 2018 summarize the argument that if you look at the ratio between 018 and 016, the climate had a sudden drop to a cooler temperature, much more increased fluctuations, and affected hominin in the sense that it had to appear a type of species, Homo sapiens, that were much more adaptable of moving, leaving Africa, going to different areas in the globe where climate was more favorable, using tools able to adapt to a high degree in climate fluctuations. If indeed this is a case, then our argument that the heliosphere was encountering a cold cloud that made the climate become much more colder will have a direct influence on human evolution. So I hope I convinced you, I'm arriving to my last slide, on the importance of breaking silos, of going between space physics to astronomy to climate. And I hope I take this research also to prior epochs in climate and also for the future to see how the heliosphere, the location in the galaxy, affected climate. And I'm showing you a picture of the Voyager team. And many of my heroes are here, childhood heroes that explore the solar system. But I'm showing that to show you that there's not much diversity. And I was puzzled when I first joined physics and space physics to realize the really lack of diversity. And as a lead of SHIELD, I'm trying, this is a bunch of our efforts to bring diversity and diverse voices to STEM, not just in gender, but in sexuality, in where you come from, to bring different voices to the table. This will make the science so much more richer and more discoveries will happen. Thank you very much. And I want to pass it to Claudia to moderate the Q&A.
Merav, thank you so much. This was endlessly fascinating. Thank you so much. As you can imagine, there are questions. And the first one is, can your research on the heliosphere give us information and guidance regarding the climate crisis?
I am completely fascinated by that. This is one of my next projects. I won't mention now my ideas, but it has an effect. You can start looking to more details on the carbon cycle, and the location where the heliosphere was in the past and will be has a direct influence. So stay tuned, more to come.
Okay. The next question. What are the implications of the shape of the ancient heliosphere on the shape of the magnetosphere?
That is, it's a fascinating question. I think, okay, so for people not familiar, magnetosphere is what comes around Earth, right? And I think people in space physics thought that the heliosphere was a long tail, came from the magnetosphere, because the magnetosphere is pretty extended, but the magnetosphere doesn't, but the Earth doesn't have a wind. So I think the main difference between the core sun and the magnetosphere is that the sun has a wind. The other topic I am fascinating is to apply this knowledge to other stars, because clearly the interplay of the wind from the star and its magnetic field is critical to the shape. And the shape is critical for the filtration of galactic cosmic rays. And as you can tell, if we were outside or inside. So it has a direct implication of climate and evolution.
Right. What are the, are there other biological samples, subsurface sediment sampling of microbes, diatoms, or other things, for example, that could be used to test your hypothesis about the Earth's encounter with the cloud, with a cold cloud?
That, again, it's a very interesting. So I am diving into this literature, and I need to talk to more experts in climate to help me navigate through that. There are other indicators. If you know, in 70 million years ago, where there was an asteroid that came, they will figure out that from DNA that was found. So I am looking to that literature to see, not just on Earth and the moon, but in any other planets as well. We would like sample returns from other planets to see the possibility of this scenario.
That's great. And the next question, I think I touched on it in the introduction, but I wonder whether you can expand on the implications of your research on the search for other habitable planets.
So, okay, so I can expand a little bit on that. When I started looking on the habitability and the effect that the heliosphere had, my focus was on the galactic cosmic rays. Because of course, this is the first thing we saw. We see Voyager leaving, the galactic cosmic ray goes up and down. But the galactic cosmic ray effect on climate, there are some studies, but it's not proven yet. They see the radiation going up and down. They see the galactic cosmic rays affecting clouds, but it's still not sedimented. So I think I am fascinated by that, how much galactic cosmic rays you needed when life even began on the Earth, because you need some radiation, but you cannot have too much. So this is all future venues that I would like to go. So I went to the first one that I thought was the most extreme, the fact that the heliosphere is modulated by the pressure, because it told me that if you vary a little bit the density, you are completely unprotected. But between this extreme scenario and the galactic cosmic rays, I think there is a whole new avenue of science that needs to be mined into really looking into the effect of habitability.
And about, looking into other aspects, have you looked at whether the solar radiation field would ionize the dense cloud out of the Earth?
So yeah, it's a very interesting question, and it does. In fact, for our current and where we are, the hydrogen come, they get ionized, and this is what heat up the solar wind. I don't think on that cold cloud, this would be an important effect. It's around, if you calculate, it's around 10% maximum because it's so massive. But if you go to intermediate densities, you really need to look on the ionization as well.
And the next question is asked for a more detailed explanation. So how is the galactic magnetic field generated? And what methods do we have to observe the distribution of the magnetic field in our neighborhood?
You know, you're asking all the amazing questions. I started thinking about it when I entered into astronomy. My PhD was in astronomy, and I was fascinated by the origin of the magnetic field. There are many, many theories of origin of magnetic fields. Are they generated by the rotation of the galaxy? Are they primordial? Do they come from when universe was formed? I think when I just have to comment that regardless of the origin of the magnetic field, and in really, really large scale, we can measure it and see that it's on the plane of the galaxy. There's some component outside of the plane, but mostly in the plane of the galaxy. The interesting thing that the plane of the galaxy is inclined 60 degrees to the equatorial plane of the sun. So where the planets rotate, we are 60 degrees. It's only we are going sideways. And so when I started working on the direction of the magnetic field, it was clear from the Voyager measurements, even before we left, that the magnetic field outside the heliosphere is not in the galactic plane. It's actually inclined 60 degrees. And so the question, that this is a whole topic I didn't touch here, is what makes a magnetic field in large scale be on the plane of the galaxy and being distorted to 60 degrees. Mm-hmm. And we actually have a lot of measurements, even galactic cosmic has really high energy, that tells us that that direction stays for really long distances. This is an open question. And how to reconcile that with what Voyager is measuring now, it's another big puzzle, because Voyager is not measuring that direction. So why is that?
Indeed. The next question is, it seems that the solar system happened to pass through the cold Leo cloud just when the Iron 60 pollution event reached us. Was that fortuitous, or are the two events actually related?
I think you're asking a question that I won't be able to answer you because it's my next paper. What made the 6 to 7 million years? So stay tuned. I won't divulge what I think it is. But one interesting story that the 2 to 3 million years ago, we tuned the speed of the cloud to encounter 2 to 3 million years ago. You could tune it a little bit that the cloud met a little bit before. What is interesting that the size of the local Leo cloud is also consistent with the width of the peak. If you look at the peak, it's pretty wide, it's 1 million years. And the size of it, it's around a parsec. So you can calculate how long the local Leo cloud will pass at is consistent with that width.
Got it. Do we know what will happen to the heliosphere next in our interstellar cloud neighborhood? Do we have any?
That is, again, a fascinating question. And we think we are between two clouds now. Those clouds that Redfield and Linsky found, the closest one are called G cloud and Lie cloud. And we think we're right at the edge in between, grazing. So in the next 10,000 years, we're going to leave this location. And the heliosphere is going to react to it. So this is a critical study needs to be done to follow the trajectory of the sun for the next 10,000 years and beyond and predict. Some people argue that we are going to go to a fully ionized cloud. If it's a fully ionized, the heliosphere is going to shrink a lot and is also going to affect incredibly the conditions in heliosphere. We need to look into it. This is a missing link that the disciplines need to work together, called climate, space physics, and astronomy, to answer that question.
Right. And following up on the previous question, I guess, is, if I interpret the intention of the audience, is there any prospects of human living the heliosphere successfully?
So can I translate your question in a different way? Are there prospects for humans living on Mars or on the moon? I wrote an op-ed with Avi Lab a couple of months ago, touching this question. Forget even leaving the heliosphere. The fact that we live on Earth, we are protected by the magnetic field of Earth. We have a secondary shield, not just the heliosphere, the magnetosphere. Earth has a magnetic field that deflect galactic cosmic rays. When you leave Earth, imagine you are living on Mars for 3 years. There is a colony. The amount of radiation that you get from galactic cosmic rays is huge, is deadly. Given the heliosphere as it is now, if the heliosphere starts expanding, we might be safe. But we need to really figure out and quantify that to be able to create shielding mechanism for humans to start exploring Mars and the moon. Beyond that, leaving the heliosphere, we are trying to have a new Voyager, an interstellar probe mission, to go and explore that region. This needs to be done. But so getting a machinery to be launched and getting there, it's a first priority. Getting the humans out of the heliosphere technologically is still hard, but we will need to quantify when we will be able to do it. We better have a good chart of the galactic cosmic ray radiation because we don't have it now.
Yeah. The next question, do you think that the movement of the heliosphere may have shaped other events deep in the history of life? For example, can you follow the history of the heliosphere more deeply, say 500 million years ago, when the end of a long ice age is thought have enabled the explosions of animals?
This is another topic that I started researching because indeed, if you look at 500, the Devonian period, there is a drop in temperature again. And if the cloud was responsible for that drop, why not another crossing? We need to, again, so then comes a question where we were in the galaxy. Or maybe it doesn't matter, we were in an interstellar medium similar to us, and the probability, and I showed you, is pretty high of meeting a cloud like that and having. So this is another avenue. I think this work opened a whole new frontier when I haven't thought that the heliosphere, before I started, will have such a direct impact on climate. That where we are located is so directly related with climate. So for me, it's okay, great, I have a new playground. I really need to dive into this data to be able to predict. I think this work show one-to-one the implication.
It is now quite a specific question. So how about the interaction with local bubble B field?
Oh, I love that I have all these experts in the audience asking me these great questions. Okay, so the local bubble, what formed the local bubble? It's an explosion of a past supernova 15 million years ago. There are some work that predicted the magnetic field in the walls will be much stronger. And for people that are not familiar with the units, when we talk about unit of magnetic field outside, we are talking 1 to 4 microgauss, okay, it's small, 10 to the minus 6 Gauss. It's a small field. But this is what we think in the universe, the field is between stars, between galaxies. The field at the walls of the local bubble is predicted to be as high as 6 to 8 microgauss. That is absolutely fascinating, because it's mean that the sun has its own magnetic field, and there will be lots of interesting effects. Like, if this is maybe too much of a jargon, but it's called reconnection, where two magnetic fields meet, they can change its geometry. What will happen? It's almost like the heliosphere with its magnetic field will meet the walls of the local bubble and maybe build a hole when two magnetics meet, when more particles will come. That is an interesting topic to explore on its own.
Absolutely. Let's get to, you touched at the end of the presentation about the interdisciplinarity and about the importance of diversity. There is a question about that. Thank you for your discussion of the importance of interdisciplinarity within science. What is your sense of where the fields are going now in science and connection to science and humanity? It seems that there is more siloing than less.
There is more what?
Siloing, more silos.
Right. I think I'm being in the field more than 20 years, and I had my share of challenges, and I think, and I had a lot of female students and male students, and it's challenging to mentor them. I think we need more female professors in STEM, definitely. We need to be more visible. We need a critical mass in departments that are of STEM with female professors and other diversities. I'm just talking about gender, but other diversities, to bring into light students that they can see somebody that they recognize. I'm part of the LGBTQ community. I see students that are gender fluid that come to me, both male, female, that come and look for me for inspiration, that this is possible. I think this is still critical, because so much of science is done in a very macho aggressive way. We need a critical mass of different ways of doing science and different just faces out there. And of course, the other diversities that I touch, I do think that science and other fields are done in silos. Look at my field, space physics. Barely communicate with astronomy. I'm always the one jumping between the two. And now I'm going to climate that barely communicated with us, and vice versa. It's not their fault, it's our fault as well. So trying to bring these communities together to tell a unified story is something that I think we all need to aspire.
Yeah. And if you can tell me very briefly, how did the Radcliffe Fellowship help you kind of meet some of these challenges? Very, very briefly. We're running out of time.
Oh, I can't tell you enough how amazing place is Radcliffe. I wish my department for the rest of my life would be as Radcliffe Institute. It's incredible to meet. I think for me, it's emphasized the value of ideas, the value of scholarship and ideas, of debate, an open debate in an unarmed way. So when you go to talks in different fields and we are openly debating ideas, it's bringing back to your own research a way of doing research, a way of doing science. So I cannot vouch enough for the beauty that is held at Radcliffe Institute.
Thank you, Merav. Thank you for your fascinating presentation and for your perspective. I also want to thank the audience for the terrific questions. I hope you'll be able to join us for other Radcliffe virtual programs. You can find out about future programs and watch videos of past events at radcliffe.harvard.edu. And with that, I'll thank you again all today. Enjoy the rest of the day. Bye-bye.